Hi, my name's Nate Greene, NASA White Sands Test Facility, and I'm involved with composite overwrap pressure vessel testing and verification of models. And so I've been working at NASA White Sands in the composites testing arena with a team of about 17 engineers and scientists.
My name is Regor Saulsberry. I work here at the White Sands Test Facility. Primary focus of my work is non-destructive evaluation, or NDE. A lot of that work is involving composite overwrap pressure vessels because that is one of the primary risk items that NASA faces in current and future spacecraft.
I'm Woody Woodworth with United Space Alliance. I'm the chief engineer for the shuttle orbiter program, so I'm orbiter based.
My name is Rick Russell. I work for the Orbiter Project Sustaining Engineering Office here at KSC, and I've been involved in the Composite Overwrap Pressure Vessel, or CLPV project, for a number of years now on two capacities, mainly dealing with the aging materials aspect of it and acting as the Orbiter Project liaison to the whole project, including the test activities that are going on at White Sands.
For spacecraft, you're looking to reduce the weight as much as possible in order to allow yourself to leave the Earth's atmosphere. So you're always looking for a weight reduction in order to get your power to weight ratio. So a good way of getting that weight reduction is to reduce the weight of these pressure vessels. So we went to a COPV, which is a composite overwrap pressure vessel. It allows you a 50% weight reduction, and in doing such, you get better thrust to mass ratio.
What we're concerned about right now is with composite overwrap pressure vessels, they're much lighter, and this is a carbon overwrapped vessel. It's got an aluminum interior liner, and they're an enabling technology for NASA because they allow us to get quite a bit more fluid onto our spacecraft and save quite a bit of weight. However, with composite, it is much more complex. There are lots of fibers and also a metallic liner, so you have two materials. And so you have more things to control in order to keep this safe than with a metal pressure vessel.
So the use of COPVs is a means in which we can carry propellant, a means in which we carry life support. For the orbiter, we use a titanium tank with a Kevlar wrap. For the future programs, they're looking at a metal tank or a titanium tank with a carbon wrap. So it'll exhibit some of the same concerns. As far as COPVs are something that we use now, we've used it on station, and we will use it on the foreseeable future programs.
These vessels are integrated into all of our NASA programs. Because of the weight savings, we are looking at, in comparison, the vessel weighs less than the actual gas or fluid that it stores. We're using these vessels for oxygen, for environmental control and life support systems, for propulsion systems, for carrying both the propellant and the pressurant fluid to push the propellant into the rocket engines. So they're integrated throughout all of our vehicles. They're also integrated throughout our international partners' vehicles. So right now we're getting ready to inspect the AMS vessels, which have them in our international partner vehicles. So also our payloads. Anything that is trying to save weight, we will put a composite pressure vessel in that application. So we must understand the failure modes and be able to mitigate the failure causes so that we have a safe and reliable vessel. Our concern is that with a composite overwrap pressure vessel, there's still a lot we do not know about these vessels, and they could explode, catastrophically explode. That is due to the fact that the overwrap is a brittle type of material and fails in a brittle manner, whereas with a metal pressure vessel, it fails in a more ductile tearing case.
CLPVs are inherently risky because because of their high pressures and because they can explode with little or no warning, and they are used throughout the Kennedy Space Center in flight hardware and flight hardware processing. During our age life assessment of COPVs for orbiter use, we examined 3 different aspects of a composite overwrap pressure vessel. The first being the actual age of the liner itself, which is a metallic structure, and problems in liners would be fatigue, and we did some analysis and determined that would not be an issue. Then there's the actual aging of the overwrap material, which in the orbiter's case is a Kevlar. And we did some studies, we did some literature research, and we actually did some testing on some new materials and actually some materials that we got from the Columbia debris, and determined that aging of the Kevlar material alone is not an issue. So that brings us to the ultimate and most risky aspect of these vessels, and that's stress rupture. And stress rupture is more a phenomenon of the whole component itself, and it's basically the fatigue life of the overwrap at pressure over time.
There's a lot of energy stored in these vessels. The vessel I'm holding in my hands contains around 1 pound of TNT equivalent energy when it's filled to its operating pressure. The vessels on the shuttle, for example, the OHM's 40-inch tanks hold about 11 pounds of TNT energy. So if they were to rupture, they would likely destroy the vehicle.
Though we've never had a failure of a COPV through service, we do know that failures can occur as we've conducted some failures in testing. And a failure of a COPV, a 40-inch COPV pressurized to 4850 psi, is the equivalent of 10 pounds of TNT. 10 pounds of TNT would result in loss of the vehicle, loss of the pad facility. So it's a very destructive force. Realize that COPVs are something that are used across in the International Space Station, not only within NASA, but we also have a lot of the foreign representatives that also use COPVs and deliver them to us, not only as a COPV, but a pressurized COPV. So there are a lot of cares that we need to take to assure that we don't inflict any damage or cause anything to cause a failure mode. And as mentioned, not only is it being used now, but it's something that will be used in the foreseeable future as a means of which we can get our propellants and our life support systems into space.
This is a vessel test of the Orion Ascent Abort component. This tank was tested this year to determine if it was susceptible to mechanical damage for the credible threats that were identified during operations. So the vessel is being pressurized after mechanical damage at the visual damage threshold to see what the residual strength of the component is. You can see some strands breaking as damage progresses through that tank composite, and the tank is pressurized with water, so it's hydraulically pressurized. In service, it's pressurized with gas, with nitrogen. So it's more than an order of magnitude more energy in actual service. The energy in this case is below 1 pound TNT energy, and you can see the damage there, and there's nothing left. And in service, you're at about 26 pounds TNT equivalents. This is the high-speed video showing how rapidly that vessel comes apart and the shock blast wave that comes out and some of the fragments. Very sobering amount of energy, and definitely shows us why we want to make sure that we understand the risks and do our risk assessment appropriately and control the failure of these components. What we're trying to do right now is we're trying to mitigate the risk in 3 different ways. One is by acceptance and ground processing. We want to be able to make sure that during acceptance we have vessels that do not have any damage or manufacturing anomalies. We also want to make sure that during ground processing we minimize risk to personnel and equipment. Then we are doing a test program, 2 test programs, to understand the reliability and life of vessels and strands. The International Space Station program is leading the effort to understand the reliability and life at the vessel level, and the NASA Engineering Safety Center is leading a program to understand the life of the actual fiber material itself. And then the third prong of our risk mitigation effort is to look at the health of the component during its operational life and through its end of service. So we'll be using all different kinds of non-destructive evaluation techniques, including visual inspection, eddy current, borescope, strain monitoring. All those types of different techniques we'll use to assess where the vessel is in its life.
One of the things, as far as the risk, I mean, the greatest risk we have is on the ground, right? Because it's when we're going through the pressurization, that's when we're fully pressurized, and as soon as you lift off and we start using some of that commodity, the risk is reduced. So, you know, like I said, a lot of the concern is what we have on the ground and the risk to the personnel there.
In order to safely use composite overwrap pressure vessels, mitigate the risk, we need to look at the full spectrum of application from manufacturing, through use, operation, servicing.
So we have 4 different areas that we want to make sure that we're paying close attention to make sure that these vessels are in a stable state, free from progressive damage. The first and most well understood is fatigue crack growth in the liner. We limit the number of cycles that a vessel sees and make sure that there is no corrosive product. We make sure that the fluids and the environment is compatible with that metallic liner. The second is overstress. We want to make sure that we do not overpressurize or overstress the vessel to break either the fibers or induce crack growth in the liner. The third is mechanical damage. We don't want to induce a mechanical damage or ding. You can see there's a mechanical damage on this vessel at 15 foot-pounds mechanical damage energy, and that mechanical damage provides a site for damage propagation. So we want to prevent that using mechanical damage control plans. And then the fourth thing we're very concerned about is stress rupture. We do not have data, don't have a good understanding of scientific data set, statistically significant data set to characterize how stress rupture affects the life of the vessels.
Well, here at the Kennedy Space Center, we're obviously concerned and careful about how we handle and work around COPVs. We handle COPVs in a variety of ways. We have new COPVs coming in here that are installed into various systems. We have COPVs that are embedded within the flight hardware, so they're part of our daily process. So we have damage control plans, and we have inspection plans where we look for things like mechanical or chemical damage. To increase the safety for the personnel and for the hardware, we have put in a few mitigation efforts here at KSC, including the way we pressurize the tanks. For example, for the orbiter, we've instituted a 2-stage slower fill for the tanks that decreases the pressure and the temperatures of the tanks to lower the risk of stress rupture. Also, we pressurize the tanks later on in the flow to minimize the exposure and the time at pressure. And also, we've minimized the personnel access. It's much more restricted now for the times and the pressures that we allow personnel to be around the tanks. We have initiated area clears during the pressurization of COPVs to help mitigate the risk to both personnel and flight hardware. Another thing that we do is we pressurize tanks later in the processing flow. For example, instead of weeks before launch, now we're just a few days before launch, and obviously this helps mitigate the risk to both personnel, the tanks themselves, and ultimately flight hardware. Specifically for the Kevlar tanks, which are used in the orbiter, we have discovered that temperature has a negative effect on the stress rupture life. So another mitigating factor that we've introduced is that we now fill these tanks with a slower two-stage process to reduce these temperatures. We've also reduced personal exposure to COPVs by filling them in remote areas when possible, and by reducing access in all of our processing facilities when they are at pressure. Because we know that pressure is also a main component in the stress rupture life of a vessel, we have mitigated the reduction of the maximum pressure of vessel C in certain cases. One of the things that we know is that the stress rupture life of COPVs is greatly influenced by mechanical damage. For example, a technician dropping a wrench onto a tank. So one of the things that we've done for all of our programs is that we've introduced damage control plans, which is especially important for all programs, including tanks that are coming in from our international partners. Because of what we've learned from the orbiter project on COPVs and their inherent risks, we're very sensitive in looking into the new designs for the Constellation spacecraft and how we would inspect, handle, and potentially monitor with some innovative new technologies in health monitoring to monitor the life of these tanks both here on the ground and during flight. And health monitoring could be especially important in the Constellation program because of the limited access that we have to these tanks and to the fact that they're going to be pressurized and used for longer periods of time in space, both at the space station and during our lunar missions.
For flight applications, we need to monitor things like pressure and strain, in addition to that, acoustic emissions of that vessel. And we need to have systems that are lightweight, don't add a lot of mass to the vehicle. So we're developing that at White Sands in coordination with the NASA NDE Working Group and NASA Engineering and Safety Center. And we have several vessels that are just going in test. We have IM-7 vessels to represent space station. We've got T-1000 vessels to represent those going into Constellation and future vehicles. And we've got conventional strain gauges, and we were installing fiber-based strain gauges, and same thing with acoustic emissions. We're looking at conventional larger acoustic emission sensor, very lightweight, small fiber-based sensors, and we can characterize the vessel health and put together a database that we can use in the future to identify onset of progressive failure in flight, and also be able to compare these very lightweight fiber-based sensors performance to conventional hardwired type technology. And this will allow us to, of course, install these, use the database, and help mitigate the risk on our flight vehicles. Acoustic emission has been, as a technique, has been around for many years. We're just trying to refine it to the point that we can really identify the onset of failure. Typically, as you pressurize a vessel, it is acoustically very active on the first cycle, and then you depressurize it, bring it up on the second cycle, and you get very few acoustic emissions until you exceed that level, that operational level. Now, if you start to get emissions during that normal level, that means that you have undergone some strand failures, that progressive failure has started. And as you drop that pressure down, bring it back up, you can do a health check and understand, it's a term called felicity ratio. If that emission occurs, at below the previous nominal pressure, you get a felicity ratio of some amount less than 1, and that's a flag that you need to look at that vessel more closely. Once you detect onset of progressive failure in flight, you need to understand how aggressive this is. Many times it's minutes, days, weeks before a vessel will fail. So based on our database, you would understand the rate of failure of this vessel and the kind of aggressive action you would need to take. If the vessel is failing rapidly, you would need to get the pressure off of that vessel quickly. You vent that. That may or may not be a problem for that particular mission. Or if it's less aggressive failure, then you would vent it down to a safe level where the acoustic emissions are dramatically reduced so you can make the vessel last through that mission. Okay, we mentioned that it's very important to inspect the vessels prior to installation in the vehicle because stress rupture will occur much more rapidly in the location where you have any type of damage, broken fiber, matrix damage. White Sands does offer a composite overwrap pressure vessel damage detection course, and it's important that personnel handling the tanks, installing the tanks, receive that training because a lot of times this damage is not obvious to untrained eye. And even beyond that, if it's a tank that's unusually susceptible to damage or that the stress ratio is high, I'd say it's important to go beyond that and use techniques like shography because that's been shown to be able to detect damage below the visual detection threshold.
Essentially, it's a three-prong approach. The one approach was to see if we could replace the tanks or inspect the tanks thoroughly. The other approach was to determine what sort of mitigations we can have to reduce the risk of stress rupture. And the final was to conduct a test program to get a better understanding of the stress rupture as a failure mode. The first part of it, the access to perform inspections or replace tanks. Ideally, that would be the situation if you could put in new tanks. That would be your best means of mitigation. Unfortunately, with the orbiter, access to all the tanks is not readily available. We had a case that we could change out some of the tanks that were in the mid-body. We had good access to that, and it turns out that some of those with the higher stress ratios were those that we replaced. And the unfortunate part is that we have some of these tanks that are in the pods, which we don't have access in order to conduct a thorough inspection or replacement of these tanks would require a complete disassembly of the pods. So that adds a concern as far as being able to inspect the pods. The other aspect of it is that the opportunity to cause damage to the tanks through human intervention has been reduced. The other aspect of it is mitigation, and the team was focused on determining what sort of mitigation plans we could put in place in order to reduce the risk to the COPVs, understanding that the greatest risk is out on the ground, so it's where you have personnel going through the processing, pressurizing the tank, working around the tank. And then the other aspect was to understand stress rupture as a failure mode altogether. With that, we've constituted some stress rupture test programs that will allow us to better understand stress rupture as a failure mode. And in doing such, we've gained a lot of insight into that to better understand stress rupture failure mode for our specific tanks on the orbiter. Once again, the future programs are using COPVs, but of a different nature. Future programs are looking at using a carbon overwrap as opposed to a Kevlar overwrap. So testing will be conducted on that to get a better understanding as far as the reaction of a carbon overwrap pressure vessel as opposed to a Kevlar.
Stress rupture are a concern for us because we do not have a statistically significant data set and we don't understand how that damage progresses. What we do know is that in the composite itself, the damage due to manufacturing or due to mechanical damage or just sustained load in time and temperature can progress and cause catastrophic rupture. We do know that it is sudden, and we do know that we cannot right now predict that damage. And so that's why we're doing a real scientific study to understand when and how does that damage start to progress and cause a stress rupture type failure event. For our test mitigation strategy, we are planning to have 2 programs. One program will be focused on the vessels and our components that we have in flight right now. The other part of our strategy is to look at the materials and a much more detailed micromechanical analysis of what is occurring for stress rupture. The first program is funded by the International Space Station Program Office, and we'll be looking at 300 composite overwrap pressure vessels, and they will be tested at various stress levels to understand when does progressive damage start to occur and are there warning signs that the vessel is going to fail. The NESC program will look at strands and resin components, and we'll put those components under stress and again look at what is the failure time, how are they failing, and do the materials, can we predict life for the component based on the life for the actual materials. Right now we do not know the answer to that, and it'd be very nice if we could just do a materials test to understand what are our life, what are the risks. So that is how we're planning to address both the details and the component level life, stress rupture life questions. In the ISS test program, we're planning to build 300 vessels, which we will instrument some of those vessels to understand how the vessels respond to sustained load and time. We will also test those vessels at different load conditions, stress load conditions, and what we'll do is look at those different load conditions, when are those vessels failing. That will give us a global idea of what is the appropriate life to use for a vessel that is around 500 cubic inches in volume. That data will also be useful in understanding scale-up. With the NESC test, we'll be looking at fundamental materials. We'll be able to look at, when we look at those fundamental materials, we'll be able to see, do the fundamental material data for load and time, do those match the vessel data for load and time? We'll build a model to tie all that data together and make it appropriate so that that model can be used to predict the lifetimes for various scales of vessels that we have across constellation, ISS, and partnership space exploration vehicles. So that's kind of how we're going to tie all this together within the models and validate those models using this test data that we're going to be collecting. These test systems that we'll be using to test the vessels are very advanced. There's never been test systems built like this before. They will allow us to measure the internal volume, the strain, and the acoustic signature of the vessels during test. So they will be able to give us a good idea not only for when the vessel fails, but also how the vessel fails.
In order to understand the stress rupture failure mode, we established a COPV working group. And really, the COPV working group had 2 aspects they were looking at, one of which is the ground processing mitigations, any efforts we could do there in order to reduce the risk for the orbiter and our current operations. And the other aspect was to understand the stress rupture as a failure mode. So we've instituted some testing to get a better feel for the failure mode, failure mechanisms, and we've conducted some testing to give us some pretty reliable numbers for the orbiter program. But understanding that this is COPVs are here for the foreseeable future, the stress rupture testing will not only be continued with on our orbiter tanks, but we've gone off and established test programs to include the tanks that are used on station and also the tanks that could be used on constellation as well. COPVs are something that will be used for the foreseeable future based on the fact that it gives you a good weight to strength ratio. But with that, there are some things that we ought to take into consideration. We mentioned the fact that the COPVs ought to be in such a position that they can be thoroughly inspected and understood. The time at pressure, the pressure rates, and all those things are things that we ought to understand and control those. Another aspect on the COPVs to be considered for the future programs is establishing a fleet leader program in which we have tanks that are on the ground that we continue to monitor and inspect and know that they are well beyond the usage of what we actually have on the vehicles. And that would allow us to foreshadow any potential problems and allow us to establish any sort of limited life that you'd have to on any of these tanks. And once again, if you have tanks that are in a posture which we can actually replace them, it may be a case that we establish a limited life and replace them on a regular basis.
The most important thing that we've learned from this test and analysis and risk assessment program is to generate your data set and your models early in the planning phase for risk assessment. We've really been challenged in this program because we're developing our models for risk assessment after the programs have already selected vessels and are already buying components. So it's been very difficult for us to provide decision makers an accurate assessment of what the risks are. So that is something that we definitely would want to do better next time.